In this video, we will learn about the important concepts of duty ratio and pulse width modulation or PWM in power converters. We have learned that the power converters achieve ideally lossless power conversion through high frequency switching, and the bipositional switch is a key element of most power converters. It's like a building block. And the bipositional switch is implemented using two on-off switches as shown here, and the electronic implementation is shown in the next two figures. This one is made of two fully controlled switches and two diodes. This is suitable for bidirectional pole current and bidirectional power flow, and the last one with just a single controlled switch and a diode that is suitable for unidirectional pole current and therefore unidirectional power flow applications. The bipositional switch is controlled by the gate switching signal Q sub A, and this digital signal can have only values of either 1 or 0. And our convention is that if Q is 1, then the top switch is on and the pole output voltage VA is equal to VD. And if Q is 0, then the bottom switch is on and the top switch is turned off. And under this condition, when Q is 0, the pole output voltage VA is 0 in both of these implementations. A majority of the power converters operate at a constant switching frequency. Now, whether we use analog PWM ICs or digital means, there is a clock pulse at the switching frequency which triggers each switching cycle. So a clock pulse here, another clock pulse here, third clock pulse here, and so on. They trigger each switching cycle, and all the other voltages and currents, they follow or they have the same frequency. Now, the inverse of the switching frequency is the switching period, or simply the period Ts. So Ts is 1 over the switching frequency Fs. So in this set of waveforms, so from here till here is one switching period Ts. Similarly, from this point to this point is the second switching period, and so on. Now, as an example, if your switching frequency is given as 200 kilohertz, then the period Ts is 1 over 200,000, 1 over Fs, and that comes out to be 5 microseconds. So for this example, this point is 0, and this point here is 5 microsecond, 1 Ts, and this will be 10 microseconds, and so on. And in the first switching period, from 0 to 5 microsecond, the switching signal Q is 1 for this amount of time. During that interval, the switch voltage, the output voltage, I shouldn't say switch voltage, the pole bipositional switch output voltage VA during this interval when Q is 1 is equal to V sub D, and for the remainder of the period Ts, Q is 0, and therefore VA is also 0 in that interval. Now we are ready to define an important quantity called the duty ratio. Duty ratio denoted by the letter D. So first we define the duration for which QA is 1 in each period Ts as the T on interval. So this is T on in the first interval, in the first period, sorry, and this is the T on subinterval in the second switching period, and so on. Now, during the T on interval in each switching period, the pole output voltage V sub A is equal to VD, and it is 0 in the rest of the switching period. Okay. So now the ratio of this T on to the complete period Ts is defined as the duty ratio D, or D sub A in this case referring to pole A. So T on over Ts is the duty ratio. Now, as we can see in these two figures, as we increase the duty ratio and we increase the T on, the time for which the V sub A, the pole output voltage, is tied to V sub D increases, and therefore the average value of the pole output voltage increases with increasing duty ratio. So duty ratio is an important factor, since in all the converters the duty ratio of the bi-positional switch, or possibly several bi-positional switches, is the main control variable to meet any given control objective. So the duty ratio will be continuously varied by closed loop feedback control to meet any objective as the operating conditions change. Now, going back to our example of Fs equals 200 kilohertz giving a switching period of 5 microsecond. So in that, let's say this T on interval. So we know that this is 0 and this is the 5 microsecond. And let's say this T on interval in the first switching period is 2 microsecond. Okay. Then the duty ratio would be 2 microsecond T on divided by Ts, which is 5 microsecond, or D equals 2 micro over 5 micro equal to D of 0.4. Similarly, in the second switching period, so starting from 5 micro, it ends at 10 microseconds. Let's say this instant is 7 microseconds. Then the D in the second switching period is also 2 micro over 5 micro Ts is 0.4. So with this background, it is easy to understand the concept of pulse width modulation, PWM, or pulse width control in DC-DC converters. So the process of controlling the average value of a quantity, in this case the output voltage of the bi-positional switch, controlling that average value by controlling the pulse width in a constant switching period. So that is called as the pulse width modulation. So in this Q sub A gate drive waveform, this has a certain pulse width. T on is the pulse width, and it has a certain value, let's say 2 microsecond under some condition. Now the corresponding V sub A also has the same pulse width, 2 microsecond T on or pulse width, and that corresponds to a certain average value indicated by this red line. So that's the average of V sub A. Okay. Now the pulse width of QA can vary anywhere from 0 microsecond up to 5 microsecond, the full Ts, as indicated by this green dotted line. So anywhere from 0 microsecond up to this entire pulse width, that is a possible value for T on. So in response, the VA also will have a pulse width, the time at which it remains equal to VD, that can change anywhere from 0 microsecond up to 5 microsecond, just following the Q sub A waveform. As a consequence, the average value of VA indicated by this red line can also change from when the pulse width is 0, this average value is 0, and it increases as the pulse width increases and reaches a maximum of the V sub D when the pulse width exactly equals Ts. Okay. So the average voltage can be changed anywhere from 0 up to this V sub D by changing the pulse width, and that is the PWM concept. Next, let's look at a few examples of PWM. The first one is an application where we have a fixed input voltage, let's say 12 volts in this example, and we want a controlled variable output voltage. So for example, in the first figure, if you want a 6 volts output, then we will be operating with a duty ratio of 0.5, such that for half the period, half the Ts, T on is 1/2 of Ts, therefore the output voltage in an average sense would be 1/2 of 12 volts or 6 volts. And if you want a higher output voltage, let's say 9 volts, then you would increase the duty ratio to 0.75. The pulse width or T on would correspondingly increase such that the average is exactly 9 volts. And as I mentioned, we will need to connect this to through an LC filter, which will remove the high frequency component, and just the DC component will be fed to the load unattenuated. Another example is to have a regulated constant output voltage as the input voltage is varying. So this is actually an animation of one of the first DC-DC converters that we'll be studying in a later video called the buck converter, which actually shows the various voltage and current waveforms seen in the buck converter. but I'm showing this now just to show the concept of the pulse width control to regulate the output voltage. So the output voltage needs to be regulated to 60 volts. This red line is the output voltage, and the green is the input voltage Vin, and that I can change by moving this slider bar. So right now it is 120 volts. So the this V sub A is the pole output voltage. You can see the duty ratio, which is this is the Q signal. It's exactly 0.5. It's 5 microsecond on interval over a total period of 10 microsecond. Now, as I increase the input voltage, let's say to 160 something, you can see that the pulse width has reduced. It's only 3.6 microsecond. So the duty ratio is 0.36, and you can see that even though the input voltage is increased, the output voltage is regulated exactly at 60 volts. And as I increase the voltage even further, you can see the pulse width or the duty ratio becoming smaller and smaller as the input voltage increases. So this change in pulse width or duty ratio is done automatically by closed loop control, which changes the D as the operating conditions. In this case, the input voltage changes. So obviously the concept of pulse width modulation is not restricted just to DC converters. In fact, you can use this concept to generate any arbitrary low frequency waveform. It's a low frequency in comparison to the switching frequency. So as an example, a low frequency sine wave generation using the PWM process is shown in this figure. So you can see that by varying the duty ratio or the pulse width sinusoidally, we can generate an average, we can generate a sine wave voltage in an average sense. So all we have to do is, let's say we are near the zero cross of the sine wave, somewhere in this region, then the pulse width is very, very small, negligibly small near the zero crossing. Whereas somewhere near the peak of the sine wave, you can see that the pulse width within, so one period is from this point up to this point. So within that, you can see that the T on interval is a very large portion. So the duty ratio is very high near the peak. So I carefully show only the positive half of the sine wave, because to generate the negative half of a sine wave, you will need, you cannot do that with just one pole, one bipositional switch as shown here. This V sub A, both instantaneously as well as in an average sense, can only be a positive voltage. So if you want to generate the negative half of the sine wave, then you would need another bipositional switch, and the difference between this VA and VB, which is the output of the second pole, that can be negative, and we can control the pulse width sinusoidally to generate a complete AC waveform. Okay, next let's look at a typical way the pulse width modulation is actually implemented. The feedback controller gives this control signal VCA based on the given objectives and the current operating conditions. But the question is, how is this control signal, which is a continuous voltage signal, is translated into a switching signal of varying pulse width to drive the gates of the bipositional switch. Now in analog PWM ICs, a ramp signal like this light blue waveform, a ramp signal is generated internally, and this is at the switching frequency. So the ramp signal starts from 0 at the clock pulse and ramps up to the final value, 1 volt in this example, at the end of that particular period. Then it is brought to 0 at the next clock pulse and ramps up again and reaches the final value at the end of that period again. So a similar approach is used in digital control implementation as well, where timers and counters are used for the same purpose. Okay, then the control signal that comes from the feedback controller is compared instantaneously with this ramp signal. So by connecting the VCA to the positive of the comparator and ramp to the negative of the comparator, so the output of the comparator, which is this PWM output, the switching signal, QA would be 1 whenever VCA is higher than the VRAMP instantaneously. and when the control voltage VCA is instantaneously less than Vramp, then the comparator output, which is QA, would be 0. So in these waveforms, starting from this point t equals 0 up to this point, let's call this as T1, we can see that VCA is instantaneously higher than the ramp signal. Only at this point the two waveforms meet. Okay? So from our this PWM implementation, the Q sub A would be 1 up to this point T1, okay? Because VCA is higher than Vramp. And after that, from T1 up to the end of that period Ts, the Vramp is actually higher than the control signal. Therefore, QA would be 0. Okay? So in response, the VA would be equal to VD till T1, and that is our T on interval, and it will be 0 from T1 up to the first end of switching period Ts. Now the duty ratio is this T on over Ts, and if you want to increase the duty ratio, then the controller would increase its control output voltage. So for example, let's say under a different operating condition, our VCA is a line like this. Okay. Therefore, the VCA is higher than Vramp up to this point. Okay. So the QA would be 1 up to this point in time, and then become 0. Similarly, VA will also be equal to VD for a longer duration and come to 0 at this point. Okay. So therefore, the average of VA, which is this blue dotted line, would also increase because of the higher T on or higher pulse width. And of course, a similar thing will happen in the second cycle as well. So QA would remain high or remain 1 for a longer duration, and so would VA remain at BD for a longer duration. So it's also relatively straightforward to derive the relationship between this control signal VCA and the duty ratio of this bipositional switch. So we can write the Vramp mathematically as shown here. So this is just a linearly rising waveform, and its slope is it actually increases by a total of Vramp peak value in a duration of Ts. So the slope is the peak value of Vramp hat or Vramp peak over Ts, that is the slope, times the time t, that is the expression for Vramp as a function of t. And at time t equals say T1, which is say this duration where the two waveforms intersect, call this as T1 in this point here. So at t equals T1, Vramp is given as Vramp peak divided by Ts, the slope, times T1. Okay. So under this condition, we know that Vramp is exactly equal to VCA. So this is equal to, and T1 is nothing but T on, right, by our definition of T on. So and this is equal to VCA because at that instant the two waveforms intersect. Okay. So from this waveform and the definition of dA equal to T on over Ts, so this is T on over Ts is nothing but D. Okay. Therefore we get the duty ratio D is simply 1 over the peak of the ramp signal times the VCA. Okay. So that is an important relationship. And in particular, if your Vramp peak is exactly 1 volt, which is what we'll be using in much of our analysis and simulations, and many times in practice as well, then this expression simplifies to D equals simply VCA, because Vramp peak is just 1 volt. Okay. So if you're using this general expression, then the VCA, the control voltage, is constrained to lie between 0 and the peak value of Vramp. And whereas if you use Vramp peak to be exactly 1 volt, then the VCA is constrained to be between 0 and 1. And finally, before we complete this video, I also wanted to highlight 2 points about the bipositional switch and PWM concept. The first is that the voltage V sub D, which is the voltage across the 2 positions of the bipositional switch, that does not always have to be a source, a DC source. All we need is for the voltage to be a fairly constant DC voltage, a non-pulsating voltage, but it doesn't have to be a source of power. Okay? So as an example, this is a boost converter, and the bipositional switch is shown here, and this is the pole. These are the two positions, and the voltage across the two positions is actually the output voltage, the load voltage. So this port actually absorbs power from this input port. So it doesn't have to be a DC source. It can actually be a load, or it can be a combination of a source and load. So the second point is the so far in all our examples, we have been seeing that we control the pole output voltage by the PWM process, and that after we remove the switching frequency component is the output voltage. That is only for a buck converter and for buck derived converters, and it's not true in general. Okay? So in general, what we actually control is the average value of the pole output voltage. That may be the output voltage, or it may be just another intermediate voltage. So again, in the boost converter example, so this is the bipositional switch, and this is the pole output voltage B sub A. So its average value is not equal to the output voltage. In fact, we control this average voltage to actually control this inductor current, which in turn indirectly controls the output voltage itself.